All right, these are the notes for 6-6. We're going to be looking at solving exponential equations using logarithms. We haven't talked a lot about logarithms since Chapter 5, but it's coming back here in the second half of Chapter 6. So for those of you who are out of class today, I wanted to make a video to help you catch up a little bit here without having to spend an additional day reteaching the same lesson that the rest of the class learned. So here we go. First of all, a couple questions here. First, what is a logarithm? Well, a logarithm, as we discussed in Chapter 5, is the inverse of an exponential function. Now, we spent a lot of time talking about inverses and how to create inverse functions. So it says, how can log equations be converted into another form? Well, let's take that in the exponential functions, something that we're used to seeing. How about just something simple like y is equal to 2 to the power of x? We know it's exponential because the input is in the position of being in the exponent. Now, if I wanted to take the inverse of that function, okay, remember the inverse of an exponential is a logarithmic function and vice versa. But the first thing that we usually do is we switch the x's and the y's. So we would switch and have x equals 2 to the power of y. Now our output is in the position of being in the exponent. Okay, this is what we called exponential form. So it's a logarithmic function, but it's an exponential form. Hopefully you remember that. We also talked about then turning it into log form. And we know something's in log form because it has log written in it. What we look for, remember, is we say log, and then we're looking for the log base. Well, that is the same as the base in the exponential form. So this is log base 2 of x should equal y. Remember, this is our way of isolating the exponent there, or getting the output by itself. This is what we referred to as log form or logarithmic form. Okay, so we will continue to practice switching between the forms to help us solve equations as we work through the rest of this chapter. Now the second question says, what do you know about the logarithm key on your calculator? Well, on most calculators, or the Inspires that we're using now, you'll see that when you type in log, it'll give you this little box for you to fill in the base. Okay, and then it'll give you another box to write in the value here. If you don't put anything in this box, if you leave it blank, it's always going to assume first that it is 10. So the logarithm keys always start with base 10. And that's why when you see a statement or something like this, remember also, if you see just log and then a number afterward here, you are to assume that that means it's log base 10. And it's talking about the little subscript 10, it's just not always written there. So when you see log base 10 of 10, that's the same thing as just log of 10, which hopefully we recognize that that is just equal to 1. But we'll work more with that there as we continue through this chapter. Okay, let's look here quickly at what we know about logs so far. They want us to graph y is equal to log of x, which is really like saying log base 10 of x. So that has an inverse that is y is equal to 10 to the power of x. That's the exponential function. And we know that that is going to have an asymptote that runs along the x-axis. It'll cross at the point 0, 1, right? Because if you put in 0 for x, we know then that y would have to equal 1. So it crosses the point 0, 1. And if we put in 1 for x, that would give us 10 as the output, so y would equal 10. So this one would cross through the point 0, 1. And we'd have the point 110. Now that's the exponential function. So that one would run right along here. It's got that asymptote. It's going to curve up here at the end, hit that point 0, 1, and then it's going to shoot all the way up to the point 110. Our exponential function, remember, is going to be the reflection across that line, y equals x. But we also know here then that if we're going to graph this function, which is y is equal to log of x, or log base 10 of x, okay, those points are going to flip. We're going to have the point 1, 0 and the point 10, 1. So instead of having the asymptote on the x-axis, this one has an asymptote on the y-axis, and it runs up. It hits that point right there at 1, 0, and then it should curl out, go this way, and that is the graph of y equals log of x right there. Okay, we'll do some more graphing as we go through. The second question here, write a general equation for y equals log of x. Well, remember that's going to be y is equal to a times log, and we'll even put base b, we'll just go with the completely general formula, of x minus h plus k, where a is our stretch factor, h is going to be our horizontal shift, and k is going to be our vertical shift. Now what we're going to be doing in this section here is we're going to be talking about how to solve equations like this. This first one here is solve the following exponential equation. 1.04 to the power of x equals 2. Earlier in chapter 5, actually it was chapter 4 I believe, we learned how to solve any equation graphically on the calculator. Remember, we can take this equation, 1.04 to the power of x equals 2, and we can break each of them into their own functions. So we'll separate it here and say that y equals 1.04 to the power of x, and y equals 2. If we graph both of these on a graph or on a coordinate plane, we can find the intersection point, and the x-coordinate of that intersection point would be the answer to this equation. So let's actually do that here. You'll see I have a graphing calculator. I've already got those two functions typed in. I'm going to graph it, and you're going to see we have our exponential graph here is the yellow one that goes up like this, and then we've got y equals 2 is that horizontal line that runs across here. So that intersection point that we're looking for here is right here. You'll see that value is 17.67, or approximately there. So that means that our solution, x, is approximately 17.67. All right, let's move on here. So one of the main parts of this section here is we're going to introduce the power property of logarithms. So what it states here is we have a log, and remember this is like base 10, even though we don't have to write that in there, okay, of some base here raised to a power of x. We can take this exponent and it ends up moving out in front and becomes a factor. Okay, so if you wanted to see another example, if we said like log, we'll even say like a different base 2 of 6 to the power of x, right? We can take that x and we can end up moving it out in front here and making it x times log base 2 of 6. Let's see how this will help us here as we look to solve that same equation algebraically. Now I've listed out the steps here so that you can write them down. You may want to pause the video, write them down real quick. The first thing we're going to do here to solve this equation is we're going to take the log of each side of the equation. So this is like an operation, and we want to make sure that we keep the equation balanced. So when you take the log of one side, you have to take the log of the other side. So I'm going to say log of 1.04 to the power of x should equal log of 2. Now, the second step, we're going to apply the power property here. So since we're taking the log of some value here and it's got an exponent, we can move that exponent out in front. So this is going to end up moving out here. So we're going to have x times the log of 1.04, and that still equals the log of 2. Third step, solve by isolating the x. Well, to isolate the x here, we want to divide by log of 1.04, and if we do it to the left side, we're going to do it to the right side. So now what we have here is x equals log of 2 divided by log of 1.04. Now this would be our exact answer here, but if we take it here and do step 4 and approximate it on the calculator, you'll see what we'll get here. So I'm going to go to my calculator again. So we said that we were going to do log of 2, and I'm going to divide it by log of 1.04. We hit enter here, and you'll see that we get 17.67 again. So this is approximately 17.67, the same thing we got when we graphed it. So this is pretty much the key steps for solving these exponential equations. One thing to note here is we always want to try to get it so that it's going to be the base raised to a power, or an exponent, and that equals the value. So if there's anything else going on, we want to hold off from taking the log of each side until we get to that point. And I'll explain that here as we go through the next couple problems. So here are 2 to practice. You can go ahead and pause the video and try to do that. I'll work through them real quick here so that you can check your answers. First one here, to get rid of the x or get it out of the exponent, we're going to take the log of each side. Now we're going to apply the power property of logs, so we're going to move this x out in front. So we have x times the log of 2.25. That still equals log of 5. And then we divide both sides by the log of 2.25. Okay, we'll get x equals log of 5 divided by log of 2.25. Okay, when you do that on the calculator, I believe that should get you approximately 1.98. You can always take it and plug it back in for x there, and you'll get a close answer. It may not give you the exact answer. All right, and then the second one here, you can go ahead and try it. After you do it, you should end up with the answer being, I believe it was, I forgot, I gotta look real quick. I think it was 0, well, you know what, let's just do it real quick. So we're gonna do log of 3.5 to the power of x equals the log of 10. Apply the power property, moving the x out in front. So it's x times log of 3.5 equals log of 10. Divide each side. So x is equal to log of 10 divided by log of 3.5. And then let's go in and look and see what that is. So we'll do log of 10 divided by log of 3.5, and it was about 1.84 if we round it there. So it's approximately 1.84. Hopefully I did that other one right there. That was the right answer. I was going from my memory, so if not, ask about it in class. We'll talk about it. All right, so then we got C and D, last two problems. Okay, now this one, when you look at C here, it's not completely in this form where we have a base raised to a power and exponent equals a value. We've got this extra 2 here. So to get rid of that 2, we're going to take it, we're going to divide each side by 2. And we now have 8 to the power of x equals 64. Now you can go ahead and finish working that out if you want to apply the logs, or the power property of logs to it there. Remember, you have to take the log of each side first. In the end, your answer should end up being x, hold on, my pen stopped working. That's not good. Well, it should be x equals 2, and I don't know why my pen's not working on here. There we go, x equals 2. For this last one here, we need to divide each side by 2. And what you'll see here is now we have x to the 8th power equals 64. So these ones here, when you compare them, the one on the left side, our x is in the exponent. The one on the right side, our x is the base. Well, we already know how to solve this. If we're raising x to the power of 8, we want to take it and take the 8th root of each side. So we're going to take the 8th root of x to the 8th, but then we also have to do the 8th root of 64 to get our answer. So we'll end up with x is going to equal, and let's see here, we should have so we're going to do the 8th root of 64, enter, and it's about 1.68. So x is approximately 1.68. So big difference here, you know, with D, we did not need to use any logarithms. This is one that you are used to doing. For C, we had to because our x was in the exponent. All right, that's the main gist of the notes. If you have questions, please make sure you mark them down, bring them to class, and we'll talk about them. All right, thanks for watching.